Bromine vapor is roughly 5 times more dense than air. It can be poured from one flask to another. The density of bromine, like that of all gases, is directly proportional to the molecular mass of its molecules in the gas phase.
All right, so this tank over here, it even sounds different when we fill it up. So here, listen to this. It sounds different. Heavy. And if you feel this, it feels heavy too. Just rock this back and forth and feel it.
Oh man.
So this is
like full of water almost.
Yeah.
Like it's got water in it because it's got weight.
And it's just gas. All right, so the same thing you're going to do, but here's what I want you to do. I want you to all your air goes out, and then breathe in, and then I want you to do the intro to the podcast. Ready? Just tell our listeners at home something of importance. Ready? All right, here we go. He's bringing in the air. There goes the sulfur hexafluoride. Right into his lungs.
Yo, y'all, you downloaded Snacks for the Brain episode 51!
See, now you can do that with some sort of... You're really doing that. You're not... There's no tricks behind the scenes or audio.
Post-production.
Is that... It's still in your lungs, isn't it?
It's still in my lungs, but it's coming out because I'm breathing.
Okay, now breathe in, and now push it back out again. You're going to have to do that a couple times because that heavy gas...
I'm almost there.
Yeah, one more. Ready? There it is.
Hello, y'all.
Ta-da! And you're back.
Jetzt eigentlich nicht mehr viel zu sagen, aber das mein Gas eingeführt. Außer es macht natürlich.
Okay, there's a lot of information in these videos I just showed, so I want to talk about it. First of all, what we're looking at here is how gas density has some amazing effects when it comes to gases. And I used to think that air, always lighter than air and stuff like that, no problem. And, helium, you let it go and it goes away and stuff like that. But in reality, some gases are much denser than like air and helium and stuff like that. And it's amazing. If you're ever around one of these gases, it literally, if you have a balloon of it, it feels really heavy. I used to use argon once in a while. Argon is an example of a gas which is denser than air we're going to talk about. And it felt like heavier. And in the one video there, the guy said the balloon felt like water. And that's not an exaggeration. It really feels different. The first video there was of bromine. Bromine in the gas phase is much denser than air. So you could see them actually pouring the gas from one container to the next. And again, you wouldn't pour a lot of gases that way, but because bromine is so heavy, you can do it, which is really cool. The second video showed the two guys, and the one guy he breathed in some sulfur hexafluoride, which is SF6. And this is another super high molar mass gas, and it made his voice go really deep. He was talking like this, and that wasn't any kind of video effect, right? That's actually a natural effect. This is the opposite of what happens when you breathe in helium. And I don't recommend this by any means, but if you're like me and juvenile always, and you breathe in helium from a balloon at a party, your voice kind of goes like a chipmunk, and it sounds kind of funny and stuff like that. Okay, well, gases that are smaller make your vocal cords get higher, so you have higher pitched kind of chipmunk voice. But on the other hand, these gases like sulfur hexafluoride, which arguably won't hurt you too bad as long as you don't go crazy with it, it has the opposite effect on your vocal cords, and it makes them go deeper. And you can see after he breathed in some regular air, his voice went back to normal, but it's kind of fun. And then finally, the last video I think is really cool. They used some kind of heavy gas. I think it's sulfur hexafluoride. And you could see that the little boat made of aluminum there actually floated on the invisible gas. It looks like it's levitation, but that's just because that heavy gas is sitting at the bottom of that fish tank, and the light aluminum balloon actually floats. But they made the balloon sink by scooping out the invisible SF6 and pouring it into the little aluminum boat, and then it finally sunk down. So it's pretty cool. Gases have just as many variety of properties as anything else, which is kind of crazy. So what we're talking about here, all these effects can be related to the density of gas, and that's the next thing we're going to look at. If you start with PV equals nRT, the ideal gas law, you can do some kind of useful manipulations to it. Moles over volume is what you get if you put the RT on the other side and the V on the other side. So N over V equals P over RT, and we're just rearranging there the ideal gas law. Now, you can substitute in for moles, you can substitute in the mass of the gas divided by the molar mass of the gas. So there's two M's right there. The little m is the grams of gas, and the big M is the molar mass of the gas. So for example, if we had 2 moles, all right, and it was helium, the molar mass of helium is about 4 grams per mole, and little m then, if we have 2 moles, would be about 8 grams. 8 grams divided by about 4 grams per mole gives us 2, all right? So just remember that little m is like grams, and big M is the molar mass, the grams per mole on the periodic table. But more excitingly, M over V, grams over liters, that's the density of the gas. So if you rearrange that a little bit, you get the density D equals PM over RT. And if you rearrange this a little bit more, you get PM equals DRT. And I like this version the best because PM is like evening, AM in the morning, PM in the evening, all right? PM equals dirt. So sometimes I call this the evening dirt equation. And yes, I am juvenile, I know, big time, but this is what helps me to remember it. And why I like this equation, and I think you should too, is it shows that there's a relationship of the density of gas D to the molar mass M. So in the videos I showed there with bromine and sulfur hexafluoride, those were hardcore, very high molar mass gases, all right? Sulfur hexafluoride and the bromine there were both about 150 grams per mole, something like that. Those are much bigger molar masses relative to helium, which is about 4 grams per mole. So molar mass of gas directly affects the density. As molar mass of your gas increases, the density increases, assuming pressure and temperature are the same. Conversely, if you have a light gas like helium, small molar mass, you'll have a small density. Density for gases usually is measured in grams per liter. So in Chem 221, we saw that liquids were usually grams per milliliter, and solids were usually grams per centimeter cubed, and a milliliter and a centimeter cubed are the same, etc., etc. Well, for gases, it's almost always in grams per liter. So if you ever have a density of the gas, make sure you record it grams per liter. Here's a question that we can use that last evening dirt equation to answer. It says, which gas has the greatest density at 25 degrees Celsius and 1 atmosphere of pressure? Okay, so this relationship is asking about the density, the little d in the last one. And you remember on the last slide, the equation was evening dirt, PM equals DRT. And in this question, the temperature is the same, the R value, R constant, 0.082057 is the same, and the pressure is the same. So what we have here is how the molar mass is directly related to the density. And the bigger molar mass will have the bigger density, the greatest density. So to answer this question, you should really go through and find the molar mass of each of those gases. So O2, 2 oxygens. Oxygen on the periodic table is 16, so 16 times 2, about 32 grams per mole. Nitrogen, N2, about 28 grams per mole. Hydrogen, about 2 grams per mole. CO2, which is a number I've just used quite a bit, is about 44 grams per mole. And xenon is actually the biggest molar mass. If you look at xenon on the periodic table, it's about 131 grams per mole. And that's a lot lot bigger than all the other gases we went through there. So because xenon has the biggest molar mass, it should have the greatest density. Xenon would be most likely to cause your voice to get deep, stuff like that, relative to the other gases because it has the biggest molar mass. Sometimes in chemistry, they talk about standard temperature and pressure, and this can be useful if you're comparing similar substances, and if they say, well, what is the volume at STP? Okay, so STP is just standard temperature and pressure. The thing about gases, though, is that standard temperature and standard pressure might not be the same as the other chapters, so FYI. Standard temperature for gases is 273.15 Kelvin, and that is, of course, where water freezes 0 Celsius. The reason why standard temperature is a little bit weird, though, most of the thermodynamic things we've looked at, so like we talked in Chem 221 about delta H with a little 0, the standard conditions. The standard conditions for enthalpy, 298 Kelvin, and I am unclear why gases have always revolved around 273 Kelvin, but they do. So just realize here that if you ever hear about STP for gases, the temperature 273.15 Kelvin, not 298. Standard pressure makes more sense, 1 atmosphere. That's the same standard pressure for the thermodynamic quantities. It's only the temperature value which changes. Now, if you have a gas at 273 Kelvin and 1 atmosphere of pressure, and you have exactly 1 mole of the gas, you can calculate that the standard volume for the gas, 22.4 liters. And at conventions, you'll sometimes see that little balloon ball there on the right-hand side picture. That balloon represents 22.4 liters. That's the volume that a mole of gas takes up under standard temperature and pressures. Now, probably that room was not at standard temperature, 0 Celsius, which would be very cold. But if it was, and it was 22.4 liters, that does represent the volume. I think it's kind of cool to see that little balloon because it does give you a symbolism as to what that volume means, all right, which is kind of interesting. But anyway, just FYI. So if you see anything about STP, it definitely means 273 Kelvin and 1 atmosphere of pressure all the time. And if you have 1 mole of gas, then the standard volume of that gas will be 22.4. If you have half of a mole of gas, though, then you wouldn't have 22.4 liters. You would have 11.2 liters, etc., etc. You can calculate the differences. The 22.4 liters is only for if you have 1 mole of gas at STP. Remembering that I'm a Star Trek person, all right, Spock had to use 2 moles of neural gas. And in an episode from the original Star Trek, Khan came and took over the Enterprise with his henchmen. And so Spock and Kirk were able to break free, and they used something called neural gas to knock all of Khan's guys out, mostly. But anyway, I digress. Focus on the 2 moles, all right? So using STP, what would be the volume of Spock's gas? So let's assume that Spock released the 2 moles of neural gas at STP, which again, 1 atmosphere of pressure, 273 Kelvin. Now you could go through and use V equals nRT over P, all right? The N would be 2, R the gas constant, standard temperature would be 273, and 1 atmosphere pressure on the bottom. However, if you also look down there, 1 mole of gas would be 22.4 liters, and since Spock used 2 moles, we can multiply 22.4 times 2, it should be 44.8 liters. All right, so that's the kind of utility for these kind of problems. It's really not about finding volumes of neural gas from Star Trek episodes, but I do enjoy talking about it, so my apologies. Let's go back to the kinetic molecular theory of gases a little bit, the KMT. And the KMT does a pretty good job with gases, but there are some assumptions, and some of the assumptions are better than others. And we're going to look at some of the places where the assumptions are kind of weak. So one of the ideas in the KMT is that gases are constantly moving around, all right? Unless you get to 0 Kelvin, there's always going to be movement. The gases will be in constant motion. And the motion a lot of times will be pretty random. And that's a pretty good assumption. I've got no problems with that. This one's kind of interesting. The pressure that arises when you measure pressure, it arises from collisions of the gas with whatever kind of walls you're containing. So if you have like the pressure from a barometer column, the pressure is like smashing into the column, making it go bigger. Pressure they feel really is from collisions of gas molecules with a container. And this actually works pretty well. So if you've ever been curious where pressure comes from, it's just from all the little gas molecules kind of smack, 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 smack on the sides of the walls. Kind of interesting. In the KMT, they assume there's no attractive or repulsive forces between the gas molecules. They also assume that the collisions between the gas molecules are elastic, i.e. no energy is destroyed. Now this one we're going to start running into some problems with. We're going to assume in Chem 222 and Chem 223 that all gases have no of these attractive or repulsive forces. In the next chapter, we're going to refer to these attractive repulsive forces as intermolecular forces. And gases generally don't have a lot of these forces going on, but there are some. And this one can lead to some problems sometimes. So just realize that it is an assumption. It works pretty well, but we're going to see that sometimes those IM forces in the next chapter can interfere even with gases. In our classes, we will assume that gases don't have these forces, but in the real world, sometimes they do. The other one, which we've already run into problems with too, is that the volume of the gases is negligible. Like we don't have to worry about the molecules. We worry about the volume the gases take up, like the liters and stuff like that. However, as we saw in the earlier discussion with Charles, as you go to 0 Kelvin, the volume goes to 0, and that's pretty lame. So the last two, there are some issues with when it comes to the assumptions. The first two are pretty good. All right. If you're curious, you can see the principal assumptions of the kinetic molecular theory handout in the companion and on the website. But you can at least start with the first two and know those are pretty good. And the next two, we have to be a little careful of, but we can make them work. We're going to take a little break into physics here for a little bit and talk a little bit more about ways that KMT can be used. But to do that, we really need to talk a little bit more about the equations used to describe the energy of the molecules and also how the energy relates to the temperature of molecules. And again, from physics, if you've taken physics, cool, and if you haven't, don't worry about it. But the energy of movement is usually seen as kinetic energy. And kinetic energy is just a type of energy. And like all the enthalpy stuff we've done so far, energy is measured in joules. So from physics, the energy of movement, the kinetic energy, equals 1/2 mv squared. And m here is just the mass. The mass is usually in kilograms, all right, or kilograms per mole. The v is for the velocity, which is like speed, how fast it's going. And speed is usually measured in meters per second. So 1/2 mv squared is the way to calculate the kinetic energy, like how many joules it's moving. But you can use that kinetic energy to also talk about the relationship of the temperature of the gas as well. And kinetic energy also equals 3/2 times RT. And this R is the energy R I talked about in an earlier slide, 8.3145 joules per mole Kelvin, and the T value is the Kelvin temperature. All right, so this line right here is just a way to see that these are ways that people talk about kinetic energy. But here's where it gets really interesting. At the same temperature, all right, all gases have the same average kinetic energy, all right? As the temperature goes up, the kinetic energy also goes up. Now, you can't change the mass of a gas, all right? Helium is always going to be about 4 grams per mole, and it doesn't matter if it's 2 Kelvin or 200,000 Kelvin, it should always be 4 grams per mole. So if the temperature changes and the 1/2 mv squared equals that 3FRST, the thing that changes will be the speed, V. As temperature goes up, the speed of the gas goes up. And as temperature goes down, the speed of the gas goes down. And I like this analogy because I feel that way in my day-to-day world. If it's cold outside and I have to like go to Mount Hood Community College to teach, like I'm a little bit more sluggish. I'm like, oh, I'd sure like to stay home today and read a book or something, you know. The temperature makes me not quite as active. On the other hand, if it's a nice day and I'm like, boy, what a beautiful day, I'm more enthused and I get ready and I get to Mount Hood a little faster and stuff like that. So I feel that as temperature changes, my speed goes up and down too. My mass does not change unless I diet, which is a whole different story. Don't get me started. Anyway, we're not going to go there. Temperature affects me. Temperature affects gases too, and it affects it through the speed. So we're going to see here in a little bit how temperature makes the speed go up, and temperature, or if a temperature goes up, and temperature, if it goes down, it makes the speed go down. And these equations right here are actually the way to get numbers out to verify that these things are happening.
Gas molecules are in constant motion and frequently collide with one another. Although not all the molecules in a gas sample move at the same speed, the higher the temperature of the gas, the greater the average speed and kinetic energy of the molecules overall. This higher level of energy allows molecules to disperse more readily, which is one reason we smell aromas better when temperatures are higher.
So this video kind of shows what I was talking about earlier, but this, instead of babbling about me going slow or fast because of the temperature, this is showing the actual gases. So as the left-hand side, you got a hot temperature, and the right-hand side, you have a cold temperature. And you can see at the cold temperature, the gases kind of go a little slower. They bump into each other, and then they go off in their own directions and stuff. But it's a much more mellow environment. On the other hand, in the left, at the hot temperature, man, those gas molecules are active and they're bouncing around, going faster, and they bounce into each other and stuff like that. Well, the left-hand side would be like me on a warm day. I'm a little bit more with it. On the other hand, the right-hand side, the cold temperature, that's me on a cold day. It takes a little bit more energy to do things and stuff like that. At the same temperature, all gases have the same average kinetic energy. All right, that's that 3/2 kT thing. But what happens then is as temperature goes up, the kinetic energy goes up as well, and that means the speed will change. The mass, 1/2 mv squared, the mass part doesn't change, but the speed will. So that's why at the high temperatures, those gases were going crazy. On the low temperature, it was much more mellow. Speed was higher on the left, speed was lower on the right. Maxwell wrote the equations that scientists still use to this day, and this is one of his equations. And you can see it's really weird. It's the square root of u squared with a line over it, and that equals square root 3RT over m. There's a lot of interesting things you can glean from Maxwell's equation, but here's what we want to realize. That u there is the average speed, all right? It's what they call the root mean square speed. And scientists use that. We don't need to worry about that right now. But think of that as the speed component, like how fast something goes. And you can see on the other side, if you get rid of the square roots, you basically square them both and get rid of them. The speed depends then on 3RT over m. Now 3 and r are constants. They're boring. But you can see that speed and temperature are both in the numerator. So that means as speed goes up, the temperature goes up. As speed goes down, the temperature goes down. However, the molar mass is a player. Molar mass is in the bottom. So what that means is small molar masses will have higher speeds. They're opposite because they're on opposite parts of the math. On the other hand, bigger molar masses that are large, will have smaller speeds. So Maxwell's equation is cool because it shows directly this relationship between the speed of a molecule and the temperature of the molecule that it's experiencing. And it also shows how the molar mass of the gas will make a speed of a gas go up and down. So speed increases with increasing temperature, and that's what we also saw in the last slide. 1/2 mv squared equals 3/2 kt. Speed and temperature were on opposite sides. Absolutely, it's going to make a big difference. On the other hand, speed will decrease as you increase the molar mass. And this may not be too intuitive, so let me use an example. Let's say that there's a runner who's Olympic quality, a really good runner, and they decide to run with me on the Mount Hood track, the Mount Hood track there where it's a 1/4 mile or something like that. And I say, yeah, no problem, all right. So I go down there with this Olympic runner, and there's no way. I mean, I'm not in bad shape, but I'm not in very good shape either, all right. And this person, if they can do the Olympics, would be really fast. So if we had a race, this person would just kick my bottom because they are in really good shape. Their mass is probably smaller, so their speed would be higher. And on the other hand, I like pizza and JoJo's way too much, so my mass is probably bigger, and bigger mass is going to have smaller speed. So you can use this idea with running, all right? Heavier people go slower, lighter people go faster. Heavier gases go slower, lighter gases go faster. So all of this is just trying to rationalize the behavior of gases and what you see when you analyze gases.
Cars on highways travel at a variety of speeds. To show the distribution of automobile speeds, we could plot the number of cars moving versus their velocities. Molecules in the gas phase show the same variability of speed. Plots of molecular speed distributions are called Boltzmann plots.
When you drive on the freeway, you certainly don't see everyone going the same speed. I like to think of myself as like a middle-of-the-road driver, all right? Like if the miles per hour limit supposedly is 65, I might go a little bit more than 65, all right? Always looking for police and stuff like that. But anyway, I'm kind of the average driver, and you can agree or disagree with me as you want. However, there's always going to be the people out there, senior citizens, whatever, and, I'm not going over the speed limit, so they go like 50 miles per hour in a 65 mile per hour zone, and it always makes me really happy, but that's another story. Anyway, they're really slow, all right? On the other hand, then there's the people that watch Fast and the Furious movies a lot more than I do, and they're just zipping by me, man. I'm like, whoa, and I'm kind of envious, but I'm also kind of like, those darn drivers. So anyway, this is all silly, but on a freeway, or any road for that matter, you're going to see a whole bunch of different speeds, all right? Some people drive hyper fast, some people drive really, really slow, but there's usually like an average speed, all right? And that probably depends on all kinds of conditions, but there will be an average speed. And in all of these discussions so far, gases are a lot like people driving, all right? Some of the gases are just going crazy. They just got tons of energy and they're just busting out. On the other hand, some of them are senior citizens. They don't have a lot of energy and they're moving very slow, but there will always be an average. And what scientists use when we talk about the KMT and how it applies to gases, we usually think in terms of an average speed. Like, what are most of the gases traveling at? What is their velocity in meters per second? Something like that. There will be gases that are slower. There will be some that are higher. But again, there's going to be some kind of average. And that that little part right there, that represents the most probable velocity of a gas, all right? And that's what we're talking about in these problems. There will totally be gases that are slower and faster, just like there are drivers that are slower and faster. But we're talking here about the average, the most likely, if you will, speed of a gas molecule. This picture is kind of cool. It shows two samples of oxygen. And the oxygen, the blue line, that represents a sample at 25 degrees Celsius. And the reddish brown line shows a sample of oxygen at 1,000 degrees Celsius. And those curves there, the blue and the kind of red-brown curve, that's just the distribution of the different gas molecules. So you can see at the blue gas, the cold gas, the average gas speed is right there. It's 400-ish meters per second. On the other hand, at 1,000 degrees Celsius, you can see that the average speed for the 1,000 degrees Celsius O2 closer to 800 meters per second. So as we increase the temperature, the average speed went up as well. However, even at the lower speed, all right, there are still some gases down here that, again, these guys really like Fast and Furious movies, I guess. But anyway, those gas molecules at room temperature are still going faster than the oxygen molecules, than a lot of the oxygen molecules at 1,000 degrees Celsius. The average has shifted to a faster speed, but you still have exceptions. And also at 1,000 degrees Celsius, you still have some senior citizen gas molecules down here that are going slow. Now you have less going slow than you did, say, at the colder temperature, which would be a bigger part right there. But you can see that the average has shifted, but you still have slow and you still have fast. And this line probably goes quite a ways out here with some small amount. So this is just showing how people think about gases, and there's always a distribution, all right? Statistics comes in really handy with these kind of analyses because you do have a variety of speeds at any given temperature. The average speed decreases with increasing mass. So remember I talked about how me, the heavy runner, would go slower than the Olympic runner, who's probably a lot lighter. This is a silly version. Actually, my example was silly. This is a practical example of how this works out. Now, again, what we have here is a bunch of distributions of speed, okay? And let's look at the averages again. Here's the O2 average. This purplish line is the N2 average. This kind of green line here is the height water average, and this is the helium average. So you can see here how the averages are moving to the right. And if you look at the molar masses, oxygen O2 is about 32 grams per mole, and N2 is about 28 grams per mole. Water is about 18 grams per mole. I don't know why I wrote water there. I guess I felt like it. Anyway, and then helium, about 4 grams per mole. So 32 to 28 to 18 to 4, and the speeds are getting larger. So that's the way that you can see that the average speed is increasing as the molar mass is decreasing. Or if you go the opposite direction from helium to oxygen, as molar mass gets bigger, the average speed gets smaller. But do realize that even heavy in this little graph thing, oxygen here has some pretty good Fast and the Furious molecules. They can probably get at least close to the average speed of light helium. So it's kind of interesting to see how this works out. In this problem, it's assumed they're all at the same temperature, whatever the temperature is, probably 298 Kelvin. So again, on average, molar mass goes up, this average speed goes down, and vice versa. It's kind of cool to see how these things work out. Diborane, B2H6, burns in air according to the equation we looked at earlier. And in this equation, there are 3 gases, all right? The B2H6, the O2, and the water. The B2O3 is a solid. These kind of rules don't apply to solids. You have to be a gas to have all this kind of cool stuff happen. But anyway, it says place them in order of increasing velocity. So increasing means slowest to fastest, all right? And to answer this question, we need to know the molar masses of the gases, because molar mass, as it goes up, then the speed goes down. So if we want increasing, which means slowest to largest, we want heaviest molar mass first, and then the last one will be the lightest one. So water is a number I know right now. It's about 18 grams per mole. And it's the molar mass we can use to figure out the speeds of these things. Oxygen is about 32 grams per mole. So 2 oxygens, 2 times 16 would give us 32. Boron, I believe, is about 11 Yes, 10.811. I'm going to use 11 because it's easier to add. Secrets of Chemist 101. Anyway, so boron, assuming it's 11, 11 times 2, 22, plus 6, about 28 grams per mole. And again, you can do better with better sig figs, but we just need to see the differences here in the molar masses to appreciate the speeds. So you can see here that the water is the lightest molar mass, the oxygen is the heaviest molar mass, and since we want slowest to fastest gases, we want highest molar mass to lowest molar mass. So I would predict here that the order would be O2, that would be slowest because it's heaviest, followed by the diborane, B2H6, because the molar mass is in between, followed by water. And lo and behold, that's exactly what we get. So you can see what we did. We went from heaviest gas to lightest gas. Heaviest is slowest, lightest gas is fastest. I didn't use super precise sig figs, and that's okay because that was enough of a difference then to show the order of the different gases. So again, notice this relationship between molar mass and speed. We'll see that several times in the upcoming discussions. Another thing to talk about with gases is diffusion and effusion. Diffusion is, I think, more practical, but diffusion is when you have two gases and they're separated by a semi-permeable membrane. And it's really hard to keep gases from each other. So what usually happens is there's some kind of small hole somewhere in the membrane, all right? And what that means then is the gases start mixing with each other. So diffusion is if you have a gas on both sides of the membrane, and diffusion represents then how they begin to mix together. Effusion is when you have a gas on one side of that membrane and a vacuum on the other. And again, almost inevitably, you have some kind of a pinhole, some kind of hole in the membrane, which allows the gas to slip into the vacuum. So effusion, you've got a vacuum on one side, and diffusion just means you have gases on both sides of your barrier. Molecules will effuse and diffuse at a speed, and the speed you can relate is basically how many moles are going through per unit time. So let's talk about that part a little bit. Rate is like a speed, and instead of talking about speeds in miles per hour, these kind of problems, we usually think about them as how many moles of a gas get you through per second or per minute, something like that. But the rate does depend on some other stuff. It depends on the temperature, so it'll be faster at warmer temperatures and slower at colder temperatures. And big molar mass gases don't get through those holes as fast as light molar mass gases do. So as the molar mass goes up, your speed of mixing, diffusion, effusion, whatever, will go down. And conversely, small molar mass gases will mix, effuse, diffuse a lot faster because they have smaller mass. So if you were comparing helium and oxygen, and again, helium about 4 grams per mole, oxygen about 32 grams per mole, well, oxygen is a lot bigger. So it will go a lot slower than helium. Helium is smaller, it'll effuse more rapidly than oxygen, assuming it's the same temperature. On the right-hand side, you can see an example with bromine. Bromine is kind of a brownish yellow gas, and it's initially in that small Erlenmeyer, but it begins to break out. I don't know if that's a diffusion or effusion, but whatever, it's getting out into the big thing. Looks like they actually took the top off, so that's no problem. Anyway, then after a while, the gas is completely distributed through the volume of the container. It looks kind of cool. Graham's law is what's used to describe the speed of effusion and diffusion of gas molecules. And the equation itself is kind of funky. The speed of A divided by the speed of B, and again, scientists use rates usually instead of speed. But anyway, it's equal to the square root of the molar mass of B divided by the molar mass of A. So we talked about how the speed is inversely proportional to the molar mass. So that's why the rate of A is in the numerator and the molar mass of A is in the denominator on the other side. But anyway, we won't really use this equation per se, but you can. It's a way to relate the rates of A versus B, and you can do that by taking the square root of the comparison of the molar masses. This is kind of a cool experiment. It puts this all into perspective. This is a classic YouTube, all right? And this isn't the cool YouTube where you watch videos of your cats making funny sounds and stuff. This is a true YouTube made of glass, all right? And on the left-hand side of the YouTube, you have ammonia, NH3, and on the right-hand side, you have a little thing of hydrochloric acid, HCl. And both of these substances can be made into a gas. All right. So we're thinking here about gaseous NH3 on the left and gaseous HCl on the right. They're on opposite sides of the tube. When the gases meet, they're going to make the solid ammonium chloride. And ammonium chloride is kind of a white solid. So wherever they mix in that U tube, all right, you're going to start seeing a solid. And the question is, like, where will the gases meet? And you can actually answer that. Ammonia, NH3, the molar mass is about 17 grams per mole. HCl, a hydrogen and a chlorine, if you look on the periodic table, is about 36.5 grams per mole. So comparing those two, HCl is a heavier gas and ammonia is a lighter gas. Lighter gases move faster than heavy gases. So what we would expect the ammonia to get to the halfway point faster than HCl. HCl is bigger. It takes more energy to get up to the top. So when the solid white NH4Cl forms, it's probably going to be on the HCl side. And that's just because little ammonia goes faster than big HCl. So you can see how this can be kind of cool from a perspective of a chemist. So in this problem, the ammonium chloride forms closer to the HCl end of the tube. And again, it just comes down to the fact HCl is heavier than NH3. So the NH3 zips to the top and then it falls down easily to the other side. We expect the white solid to be mostly on the HCl right side.
On the right is HCl gas, and on the left is NH3 gas. Where the two meet, a reaction occurs producing ammonium chloride gas. The reaction occurs primarily on the right because NH3 is lighter and diffuses faster.
Some of the HCl probably did have enough energy to go to the ammonia side first, all right? But most of it, by far, is on the right side. And the part that we can visibly see, which is going to be many moles interacting, definitely all on the right side. So this is how molar mass can help scientists to determine where equations are going to happen, stuff like that. The last thing we're going to talk about here real fast is what happens when you have deviations from ideal gas law. In certain circles, ideal gas law is seen as this fantastic, perfect law that does wonderful things. And ideal gas law is really cool, no question about it. But there are limits to what the ideal gas law can do. And if you ever plan on working in industry, you might run into some of these so-called deviations from the ideal gas law. And most of the time, the deviations from the ideal gas law, the reason it doesn't work real well is because, first of all, real molecules have volume, and ideal gas law just assumes that they're really small. The other reason, though, is that molecules will always have, a little bit anyway, of intermolecular forces. These are the forces that happen between molecules, and they're useful, we're going to see in the next chapter, to understand why gases form liquids. Like, if these intermolecular forces weren't around, the gases would never form liquids again. They'd be gases forever and ever and ever. But they do form. They're very, very weak, but they do happen. So for both of these reasons, that's why sometimes PV equals nRT doesn't work real well. In the lower right-hand corner is an example of a graph, and it shows on the y-axis PV over RT, all right? Now, ideally, if this was an ideal gas law, everything would have a value of 1, all right? So PV over RT, if you had 1 mole, all right, then it would be just right across. But you can see at the different temperatures temperatures there. 200 Kelvin is really far off from the dotted line, from the one line. 500 Kelvin is somewhat better, and 1000 Kelvin is even better. So one time that ideal gas law breaks down is just under low temperatures. Low temperatures really don't work too well for ideal gases. They have the most deviation, i.e. they're farther from that one line. The other time you will see it sometimes is high pressure. All right, at lower pressure, usually think the ideal gas law works pretty well. But man, in high pressure, that's when the intermolecular forces start kicking in and they start to show some really weird things. So if anyone, including me, the instructor, ever asks you when the ideal gas law is most likely to break down, you should answer at high pressure and low temperature conditions. This guy named van der Waal created the van der Waals equation, which is one of the best examples of an equation which tries to compensate for gases misbehaving basically at low temperatures and high pressures. So the van der Waals equation is just one equation which tries to compensate for when the ideal gas law breaks down. There are other equations like this, but van der Waals is kind of famous. So in the van der Waal equation, you have a PV equals nRT type expression, but they're adding a term to the pressure. It's n squared over A divided by V squared. And that was van der Waals' way of trying to compensate for those intermolecular forces. And again, we'll talk about intermolecular forces a lot in the next section. And that V term, it was trying to compensate for the actual volume of the molecules, which the ideal gas law kind of breaks down. So van der Waals is used a lot under these low temperature, high pressure conditions where sometimes ideal gas law would break down. Now, van der Waals introduces two new terms, A and B. A and B both depend on the kind of gas you have, so there are some typical A and B values up there. If you have a gas not listed, you can calculate what the A and B values are, and there's ways to do that. On the left-hand side is just an example of a problem I found for a tank of chlorine gas. And if you have a tank of chlorine gas, 8 moles in a 4-liter tank at 27 degrees Celsius, the ideal gas law, P equals nRT over V, it would expect to have a pressure of 49.3 atmospheres. But if you use the van der Waals equation, it comes out to be 29.5 atmospheres. And supposedly under these conditions, 29.5 is a better representation of the pressure in the tank than 49.3. I'm not going to ask you any questions about van der Waals equations, like how to calculate it and stuff like that. Van der Waals is a very specific kind of equation for a specific set of problems. I wanted, though, to talk about how there are other equations out there to help the ideal gas law if it kind of breaks down. And van der Waals is one of them. There are other ones out there. So you might see one of these one day. Maybe you won't, but you're good to go. That's the end for Chapter 9. I really appreciate you taking your time and spending it with me here. For more ways to get assistance, there's a study guide in the companion and online, which is a bulleted list of the highlights from the different sections. I recommend you go through them just to make sure you're good to go. There's also a concept guide, and concept guides have worked problems relating to the materials we've just seen. So if you're curious about how to find moles from PV over RT, that kind of thing, the concept guide might be a good place to go. Following these notes, there's a page of quote-unquote important equations, and there's quite a few from this chapter, so that might be a good overview. And then after that, I do have some end-of-chapter problems. There's some questions, and the next slide has answers. I recommend you try the problems and stuff on your own, see if you get the right answers and stuff. You'll be good to go. If you do have any questions, absolutely email me. I'm happy to help. You can also talk to the Learning Success Center /Avid Center at Mount Hood Community College. They are here to help you too. You're going to get this big time. All right, good luck with your studying. Have a wonderful day.